Friends, good evening. Welcome to 360DigiTMG. Today we are going to discuss about LLM interference. Okay, interference runtime. So here, firstly, we will understand about how we are going to have an inference. Okay, so for that, we'll have a look on how we'll get the generated inference runtime. So our large language model will generate human-like text. It will generate human-like text, or it will generate content, as in we can say, through a process, and whatever the process it is requiring for generating the output, that output is called as what? The duration of that generating the output, that output is called as generative inference. Okay. So how it will generate? What is the process? So it will involve using a trained language models, trained large language models to generate text, to generate content, to generate any languages. If you want to translate languages from one language to the another language, for that, for question answering, for performing a different task as an input, whatever the input prompt or input question a user will ask, according to that, it will process. Okay. After that, we'll have generative LLM inference generates the text output given by the input prompt. Whatever the input prompt will be given. According to that, by iterating and predicting the next token in a sequence format, it follows what? Sequence to sequence architecture. Likewise. Okay. So here, what are the key steps? So first, we will have our first input. Whatever the user will ask us, that will be our input. Then our input will be gone to our pre-processing. In the pre-processing, our input is cleaned and prepared for the model. How it will be cleaned? So it will form some chunking. We can form the words, whatever the sentences are. We can have one chunk. Okay, we can have some chunk. We can make some chunking of that words. After that, we will form one embeddings from that chunks. Okay, words and phrases are converted into the numerical representations. Whatever the words or phrases, as in the form of chunks we have created. Okay, here in the pre-processing, everything will be cleaned. Okay, like stop words, everything will be removed. After that, we will form the chunking. Okay, after chunking, we will form a numerical representations of the words and phrases. After that, it will go to a LLM neural network. Okay, in the LLM neural network, whatever the inputs are, it will process within the multiple layers, multiple hidden layers. After that, the output will be generated. The model will produce text or the other outputs based on its understanding. Okay, it will based on the model's understanding, which parameters the model has been trained on. Likewise, whatever the data set model have inbuilt in the LLM model neural network have. Okay, so it will take that input, and based on the understanding upon the model, it will generate the output. Then we'll have model size. Larger models will generally have longer runtimes. It depends upon what? It depends upon hardware also. Like if we are using GPUs or TPUs, it will significantly accelerates the inference time as compared to that of CPUs. Then task complexity. Tasks like translations or question answering can take longer time than the simple text generation or summarizations. Okay. So this is the thing. Then what we can do for that? How can we reduce the inference time? So for that, we have a optimization techniques. So here we have few techniques like quantization. Quantization is when we are trying to reduce the model precision. Okay, here what will happen? Here it can speed up the time. It can speed up the inference time, but with the minimal accuracy. Okay, loss with the minimal accuracy loss. Okay, then we have proning. Proning, what it will do? Proning means removing less important connections in the model. Okay, we are removing the connections which are not that important. Okay, and it can reduce our computational cost. Okay, so that what will happen? Our inference time will reduce. So these are the techniques to reduce the inference time and generate the output as early as possible. Then we have a knowledge distillation, wherein we'll have a teacher-student architecture. Okay, so it will transfer the knowledge from the large model, like a teacher model, to a small model, like a student model. So this will be a faster model since the large model has been trained on a big, like more data set, and the smaller model, which is a student model, which is trained on less parameters, but significantly it has been trained, it will take inference from the large model itself, a teacher model itself. Okay, and this will make faster. This will make output faster. Then we'll have a neuromorphic computing, which will have a which will have our hardware specially designed for a neural networks. Okay, this is the thing. Then here's a breakdown of our LLM inference during runtime. So first, what will be there? First, there will be an input processing, as we have seen. So a user provides an input such as questions or prompt or a text snippets. This input is pre-processed, which may involve tasks like tokenization, which may include tasks like cleaning. Okay. And after getting our embeddings and other things, what we'll do and converting into a like a format which our LLM models can understand. Okay. All these are like questions or prompt or text snippets. These are all the textual unstructured data, which we will clean that data. We will form chunking, we will form embeddings, we will clean it first. We'll remove stop words and everything from here. Okay. And after that, we will convert it in a form that our LLM models can understand. After that, we will send the cleaned, whatever the embeddings are, we'll send it to our model inference. This pre-processed input is then feed to a LLM model. The LLM will perform computations based on its internal parameters and training data. Okay, based upon what are the hidden layers, what are the parameters it has been trained on, it will go through all the layers. These computations can be computationally expensive, depending upon the model size and complexity. Then, after that, after our model has been trained, it will generate an output. The LLM will generate an output such as a response, okay, to what? To what? To the questions which user have asked, okay. A translation of a text or a continuation of a creative piece. Whatever the user have asked us to make or generate, that will generate it as an output. The output is a post-processed, which may involve tasks like formatting, de-tokenizations, or error checking. Okay. Then we'll have a interaction and feedback. Okay. Like a user will receive an LLM output and interacts with it, potentially providing a feedback or further inputs, just like our ChatGPT or other chatbots do. Okay, whenever we will give some inputs, okay, like a prompt or a question or a text snippet, whatever, it will provide us as an output. And then they ask us, okay, is this solution good for you? This will solve your problem or not? Then we can have another like question. Okay. So likewise, these feedbacks can be improved, can be used to improve the LLM performance over time. Okay. So our ChatGPT is also one of the generative model. So here, typical runtime. So if we run it in a CPU, it will take 1 to 10 seconds per inference, depending upon the model size and task. Okay. And when we are using a GPU, it will take significantly 0.1 to 1 second per inference. And when we are using a TPU, it will take 0.05 to 0.5 seconds per inference. Okay. So these are the time when we are like shifting from CPU, it is taking more time as that of GPUs and CPUs for generating one output or generating one inference at a time. And depending upon, as we have said, depending upon the model size and complexity of the model, the time will vary. Then these are some of the challenges. Challenges of runtime LLM inference. Okay, so we'll have a computational cost. Like LLMs are computationally expensive to train. Okay, that is why we generally use a pre-trained model. Okay, so LLMs are computationally expensive to run, requiring specialized hardware like GPUs or TPUs. This can limit their deployment in resource-constrained environments. So this is one of the challenge we have. Okay, then there is latency. So runtime inference can introduce latency, especially for large or complex models. This can be problematic for applications which will require a real-time response like chatbots. We'll require a real-time response. So for that, if we'll have a runtime inference, which will be more, if like we are using a very large or complex model. So for that, it will not work for a real-time application. So this is like one of the challenge. Memory footprints. LLMs have a large memory footprints, which can make it difficult to deploy them on a devices which is having a limited RAM. Okay. Since LLM has been trained on huge, vast numbers of pre-trained data sets. Okay, like all the data sets, it will have collections of from various sources. Okay, so it can make a if we are using a limited RAM, then like we are using a CPU or a limited RAM, then it will not work for us. It will be difficult to deploy on that environment. Strategy for efficient runtime. What we can do, okay, to efficient our runtime or to like quickly, like our inference should be quicker. So for that, we have a LLM inference. We have batch model optimization. As we have seen in the previous slide, we have quantization technique. We have proning. We have a knowledge-based distillation. These techniques we can use to reduce the model size and computational cost as well, without sacrificing on our accuracy. Okay. Yes, we will lose some of the information by using the quantization, proning, knowledge distillations, and other things. Since these model, what we are doing, we are trying to reduce the parameters within the LLM. Okay, so that will what it will generate an output quickly, but the computer like by sacrificing without sacrificing on accuracy. They are saying without sacrificing on accuracy, but if the user will ask questions out of the context, which we have removed from our like parameters, which we have removed from our data set, so it will suffer in that cases. Okay, so this is the thing. Then there is batching. Batching is when processing multiple inputs together can improve efficiency by utilizing the hardware resources more efficiently. Like if we'll send in batches, our input, if we are sending in a batches, that can improve. Okay, and that can improve efficiency and by utilizing a hardware resource more effectively. Then we have caching. Frequently used model components can be cached in memory to reduce the need for repetitive computations. Okay. Then we have a specialized hardware, which will be using for utilizing a specialized hardware. Like we can use GPUs or TPUs specifically for deep learning models instead of using a CPU that can help us improve performance. Okay, so examples of runtime LLMs inference. We can use it for chatbots. Okay, LLMs can power chatbots that provide human-like conversations and answers, like answers to the users in the real time. Okay, like we can use it for machine translation. If we want to translate from like Korean to English, from French to English, or any language, we can use that. Okay, even if we want to translate from text to speech, we can do that. Okay, so LLMs can be used for real-time translations of text or speech, enabling the communication across its language barriers. Okay, then we'll have personal assistants. LLMs can be integrated into personal assistants like Siri. We are using it. Siri, Alexa, all these things are what? These are one of the chatbots only. Okay, we are asking questions in audio, in like a speech format, and it is taking the things and it is giving us the output, providing more conceptual or informative responses. So what I'm trying to say is all these like Siri, Alexa, Chat GPT, all these are what? These are one form of chatbots only. Okay, so these are what? These are the generative chatbots. We have a response-based chatbots. We have a generative-based chatbot. So these are what? These are the, like chat GPTs are generative chatbots. Then we have a content creation. LLMs can be used to generate creative text formats like poems. We can give a prompt like I want to we can have a prompt like I want to write one poem on a pen or a pencil or on a school. Likewise, we can create or generate codes from there. We can use scripts. Nowadays, scripts are also generated from ChatGPT or any platforms, any like LLM models by using the musical pieces and more. Okay, so these are all the examples. Okay, so overview of all our inference in LLM. What inference in LLM is actually? So the term LLM inference can have a few different meanings depending upon the context. There are two of the most common things here. First is our catastrophic interference in LLM, and second is our interference between multiple LLM inference requests. Okay, so first we'll understand about catastrophic inference in LLM. So this is a phenomena where an LLM forgets previously learned information, where it is trained on a new information. It can happen because LLM typically uses a technique called backpropagation to learn, which can override the existing memories in the model if they are not reinforced frequently. Like our LSTM model does, like long short model does. Okay, it will have forget gate, it will have input gate, it will have output gates, likewise. So it will forget the information from the past itself. What the catastrophic inference in LLM is doing, it is forgetting all the previous information from the past. It is taking freshly new information, okay, and it is updating a current cell state. And then it is going forward and generating our output. So this is one way. And then we are having inference between multiple LLM inference requests, wherein what we are doing, we are taking multiple requests are made to an LLM at a time. Okay, multiple requests. Like we are taking multiple inputs at a time. There is a risk that the outputs of the model will be inferenced with each other. Okay. They can mismatch also since we are taking multiple inputs at a time. So this can happen because LLMs typically have limited memory. Okay, this is one of the things. And the model may not be able to keep track on a context of each request separately. Since we are taking multiple inputs at a time, okay, and we have a limited memory in the sense we can't store all the previous memory in the forget gate, and we can't like we will update the gates, and only like our sequence to sequence model or our transformer model does. It will have a attention mechanism. Okay, so it will take information from the first input. Okay, it will form like all the interpretations will be formed, and then it will form a multi-head interception or multi-head attention mechanism, wherein we will take only the most important. We will give the important score to particular input, and we will only head forward that important score to a multi-head attention mechanism. Likewise, we can do. Okay, so this is one way. This is a inference between multiple LLM inference requests. Okay, so these are two techniques wherein we are using a catastrophic inference in LLM, where we are what doing? Where we are forgetting all the previously learned information. Okay, and we are freshly taking new information at each time. Whenever any user is asking us, we are removing all the previous information. Okay. An inference between multiple LLMs means here we are taking multiple inputs at a time. So with the limited memory, we are trying to make a context. So the context should not mismatch between our interference. That is one thing. Okay. So this is it for today. So we have understood about what is LLM, what we have understood about today. What is LLM inference? How we can reduce our LLM inference time. Okay, the general key steps, how our model is getting input, and how we are going pre-processing, embeddings, then processing, and then generating our output. And we have understood about like few optimization techniques. Okay, from where we can what? We can reduce our inference time and generate our output quickly. So these are some of the techniques like quantization, pruning, knowledge distillation, neuromorphic computing, likewise. Okay. Then we have understood that, okay, when we are using a CPU, it is taking more time for inference. Okay. So if we use a GPU or a TPU, it will be good. So these are some of the challenges that we are facing. Okay. That runtime hardware issues. So we can use GPU or a TPU so that our model will quickly give us an output, and it will depend upon like how many parameter it has been trained on or which model we are using. Okay. So these are some of the strategies for efficient runtime, how we can reduce our runtime and give us the output as quickly as possible. So these we have understood about the model optimization techniques. We can use batching, we can use caching, we can use specialized hardwares like GPUs and TPUs. And these are some of the examples that we have understood for reducing which we are using for LLM inference. We can use it for chatbots, we can use it for machine translation, we can use it for personal assistance. Okay, we can use it for making a content or content creation. So we have understood about, okay, there are two methods for LLM inference. Okay, first is our catastrophic and second is our inference between multiple LLM inference. Okay, so this is it, guys, for today. Thank you for joining. We'll meet you on the next lecture with new topic.